Okay, so hello and welcome to this video tutorial for R.C. Hibbeler's Engineering Mechanics Statics textbook. So we have this problem from chapter 2 here, which is asking determine the resultant force acting on the hook. So this problem kind of combines some ideas that we've learnt previously in chapter 2. It's combining this idea firstly of handling vectors in 3D space. So previous problems might have just had one force acting and we need to determine its x, y, and z components. In this case, we've got two forces, okay? And this is where the second idea comes in of just adding forces together. So when we've added forces together in previous problems, it's been in 2D space. How we might typically add two or more forces together in 2D space is that we might decompose those vectors down into x and y components or horizontal and vertical components, and we would then add those components together respectively to give the components of our resultant force. Here it's the exact same thing, it's just we've got this new dimension now, we've got this z dimension, so we really want to decompose these 3D vectors into x, y, and z components now, and then add them together. So let's go ahead and do that then. Let's pull up a black pen here, if it'll let me. Okay, let's start with F1, so we can say F1, comma, x, or the x component of F1. Let's have a look. Well, evidently this force is acting kind of in line with the YZ plane, so it doesn't have a x component, essentially. Its y component, F1, comma, y. Well, to determine that, we have this kind of 3, 4, 5 triangle idea here, essentially saying that, you know, for every 5 it's acting in its direction, in the direction of the vector, it's acting 4 across and 3 up, right? So we can say that in terms of its y component, it is 4/5 of its magnitude, and its magnitude is 500, so we can say this is 400. F1, comma, z, using the exact same idea, we can say that this is 3/5 of 500 or 300. Okay, F2 might be a little less intuitive, I suppose. So we have this 800-pound force here, and its position is described using two triangles here. This 30-degree kind of triangle here, and this 45-degree triangle here. Let's start out by drawing some axes here. What am I doing? What's going on? So I've got some axes here, and we've used this method in previous problems before, where we say our horizontal axis here can be considered as the XY plane, and its vertical axis here can be considered as the Z axis. And evidently, it's acting in the negative Z direction, and it's acting, I suppose, in the positive. Well, it's acting in the negative Z direction, and it has a 45-degree angle with the Z plane. So if we wanted to show this on our diagram, on our axes, it might look something like this, right? Where there's this this 45-degree angle here. Let me just label that up, 45 degrees. And we can describe this as F2, or 800 newtons. Let's just add the 800 magnitude here. And using this kind of decomposition idea that we've done previously, we can say that F2, comma, xy, its horizontal component, I suppose, is going to be 800 cos 45, and its z component, or its vertical component in this context, is equal to 800 sine 45, or minus 800 sine 45, I should say. Okay, we can move on and draw some new axes, a new set of axes here for where we've got x and y on our horizontal and vertical axes. At this point, we're kind of considering this triangle here with the 30-degree angle. So we can say then that this is acting 30 degrees above the x-axis. So it might look something like this. We've got 30 degrees here. And this arrow here is effectively equivalent to this line here, which we've determined earlier to be the xy component, or 800 cos 45. So let me just add that to the diagram here. So we can say this has a magnitude of 800 cos 45. And I haven't labeled up my axes here. I can say that's the y-axis, that's the x-axis. We can say then that F2, x in this context can be 800 cos 45 cos 30. And we can say its y component is going to be 800 cos 45 sine 30. Simple stuff. Okay, so we have the x, y, and z components of each of our forces, F1 and F2 here. So now if we want to determine the components of our resultant force, we just need to add them together respectively, right? So let's just draw a division line here. So we can say then FR meaning resultant force here, comma x is equal to 0 plus 800 cos 45 cos 30. Let me just check my numbers here. So this takes a value of 489.9. FR comma y, this is going to be equal to our 400 plus our 800 cos 45 sine 30, which is going to, let me just write this out. So 400 plus 800 cos 45 sine 30. And when we bung this in our calculator, we find a value, I believe, of 282.8. And for our z component, we're adding this 300 here to this minus 800 sine 45. So we can say f r comma z equals 300 minus 800 sine 45, which, when I put in my calculator, gives a value of minus 567, minus 565.7, sorry. Okay. So we have our x, y, and z components of our resultant force here. Let me just underline them in red. We have our x, y, and z components here. It's asking, or the question's asking, determine the resultant force acting on the hook. Perhaps this question could be phrased a little bit more specifically, but the way I interpret that is it's also asking for the magnitude of this force here, of this resultant force. How might you determine that? Well, you can just use Pythagoras' theorem, right? So we can say that the magnitude of FR is equal to the square root of 489.9 squared plus 282.8 squared plus 565.7 squared, which when I bung in my calculator takes a value of 881.4. I guess we can assign a unit to it as well. We can say this is pounds. And there we have it. Awesome. So if you have any questions or comments about this problem, please feel free to leave them down in the comment section below. Otherwise, thank you very much for watching.